It's great to be here at the Keen 2021 conference. I'm delighted to share a story with you today about a neurosurgical journey of something that we have been doing for a number of years. And these developments that I wanted to share with you are really based on the entrepreneurial mindset that the national conference is all about. So the story really starts at the Keen National Conference in 2011. I was fortunate to be able to present at 2011, and I discussed many of the different technologies that we were developing at the Mayo Clinic Division of Engineering. We do about 900 projects per year, and I shared a number of stories about that and how we developed those and what some of the outcomes were. The meeting at the Keen National Conference was fabulous. The people that came were really tremendous. And now I'm very, very happy to be a part of the 2021 conference. So now I'm presenting 10 years later. And the Engineering Unleashed motto is really tremendous. And today I'd like to take a deep dive in one of the technological areas that we have been working on, and that's deep brain stimulation. So a little history. So the discovery of deep brain stimulation was really by this gentleman, Professor Bennet, MD, PhD. He's a physician as well as a physicist. He has a laboratory in Grenoble, France, which I will talk about in a little bit. But he was involved in a serendipitous discovery that became a major treatment since the mid-1980s. And he's a neurosurgeon. And so he was operating on a gentleman with a substantial problem. And during the operation, unfortunately, there was a bleed. And so when one is working in the brain, it's sort of like operating on Jell-O. I mean, it does not have much substance. And if there's an issue that you nick an artery, you start bleeding, and there's really no way to enter into the brain and work on it, because you would just create so much damage. So Dr. Bennet did what one is supposed to do in these cases, is close the brain back up and see if that would stop the bleeding, and close the rest of the patient, the scalp, and have the patient recover before anything else is attempted. But upon recovery, what became apparent is that the person no longer had the neurologic symptoms that they came in for the first surgery. And so Dr. Bennet was very intrigued by that and started researching it and developing theories, and came up with the idea that really what they were doing is disrupting the activity of that part of the brain, and comparing that to cardiology with the cardiac pacemaker. He started experiments in animals, of course, to see if indeed that could solve the problem without the major surgery and the issues that could happen during that. And so this became deep brain stimulation. And so what we have is we have an implanted stimulator, which basically is a pacemaker in the cardiac area. There's an electrode that runs up through the neck, over the scalp, and then comes into the part of the brain that needs to be treated. And if one is trying to work on Parkinson's disease or dystonia or tremor, there are very specific areas of the brain that one would insert these electrodes. And by the battery and pulse generator that is down here, it would have the effect of stopping those movement disorders. And so with that work, people looked to see if there are other things that this technique could be used on. And so at this point in time, emergency treatment for epilepsy, Tourette syndrome, obsessive compulsive disorder, depression, chronic pain, and spinal cord injury. And the comments in the parentheses are that part of the brain that is targeted for this. And if one is in the operating room, we were working on someone with Parkinson's, and we put in an electrode, and when we got to the area that was causing the problem, we actually, upon amplifying the signal, had a pulse sound that was completely duplicated by the movement of his hand, which was affected. And so by putting the deep brain stimulation electrode in that position and providing a pulse, it's rather remarkable. His Parkinsonian movement, his tremor, just stopped. It was truly amazing. And so we see that there's a lot of work going on in deep brain stimulation, and many patients a year are actually treated with this technique. So the story also goes back a little earlier to 2005. And so this is founding the Neural Engineering Laboratories at the Mayo Clinic, of which I'm a co-director with Dr. Kendall Lee. So in 2005, there I was minding my own business, sitting at my desk working on the computer, and I noticed a shadow. And I turned around to look, and there was Dr. Lee. He had sat down, at a chair by the desk, and he looked at me and said, "People tell me I should talk with you." And so we made the introduction, and we discussed a number of technologies and things that he wanted, because he had just arrived from Yale, and he was going to be starting up his research laboratory as well as a clinical practice. And the question really was, what would be something that we could help support? So with the Division of Engineering, I had 67 engineers, and we worked on multiple projects. And we could take a risk with some. I mean, at the end of the day, we need to show the value of the work that we're doing, but also we're there to try things new, provide services for patients that they would not be able to get any other way. The motto of Mayo is that the patients come first, and so that is something that we were really talking about here. When he first came in to talk with me, he wanted to do some laboratory robotics, or actually surgical robotics. And I asked the question, well, is that really going to change the practice of neurosurgery? And the answer was no. It would improve outcomes. It would reduce the time. It would reduce variability, a lot of things that it would do, but it really wasn't going to make a sea change. And so then we started talking about other aspects that he had been working on. And that was deep brain stimulation. And the thought that he had was, perhaps we can use deep brain stimulation to attack other problems of patients, not just the movement disorders, but perhaps psychiatric issues. And so there's a variety of psychiatric issues, such as, let's say, depression. Profound depression is just an absolute difficult problem. And it's very hard to treat. And so we knew from previous work that others had done that there are areas of the brain that you can stimulate and the patient will be happy. I mean, their house could be burning down, but they would still be happy. And so that's an interesting thought. Okay, so we have an area that you stimulate and you change mood, perhaps by using deep brain stimulation and monitoring it, we could figure out how to increase the dopamine level in the brain and bring people out of depression and maintain that treatment. And so what we needed to measure the neurotransmitters, and then we needed to feed back to a computer that would be embedded in the person to keep the dopamine level at a range in the normal range, and not let it fall to such a low level that they are incredibly depressed. So in terms of what I could do in that, is that I offered staff, our engineers, laboratories, and funding, which when one first arrives at their new position, they don't have. And so we became co-directors, and we have been working together since 2005. So the collaboration that we needed comes from a vast variety of sources. We need people with similar backgrounds and backgrounds that are providing skills that are needed that we don't have. And for instance, examples of the people that we collaborate with would be neurosurgeons, neuroscientists, electrical engineers, chemical engineers, mechanical engineers, software engineers, physicists, and the people that we would select in terms of senior collaborators are very critical for the direction of the laboratory, providing the vision, external relationships, working on internal relationships, funding, and direction for the laboratory. So we need all sorts of staff in order to make this happen. In fact, the list for our deep brain stimulation for creating a wireless control system is much greater than that. So in the medical arena, you've got the neurosurgeons, the neuroscientists, cell biologists, neurologists, radiologists, operating technicians, electrophysiologists, a variety of external medical collaborators, lab technicians, surgical technicians, PhD candidates. And on the engineering side, we've got senior engineering managers, project managers, engineers, chemists, programmers, technicians, machinists, designers, glass blowers, and a whole variety of students that may be from high school through graduate school. I think this is a great example, which I did show back in 2011, about our work. And so we have two scientists or engineers, and they look like engineers to me. And then we have basically the equations of what's going to happen. And then it goes, then a miracle occurs. And the one gentleman says, I think you should be more explicit here in step 2. So I think that's really explains what we do. If we look at the timeline for the Neuro projects in 2011, we had a pretty short list. So 2011, we were expecting to have our laboratory prototype of the neurotransmitter detection system prepared. 2012, we were going to have a wearable system to corroborate neurotransmitter levels and clinical outcomes. And 2014, we expected that we'd have an implantable closed-loop system for animal testing, not human testing. But the idea is that we needed to prove what it is. However, life does change when you start out on a road to discovery and things happen. So the first thing that we discovered is that we needed to create an integrated circuit for FSCV, fast scan cyclic voltammetry. This is an electrochemical technique that allows us to measure the type and concentration of dopamine, serotonin, all sorts of neurotransmitters. And so this is a 4-channel device. The actual dimensions are on the order of 5 by 6 millimeters. And it contains actually 4 of these devices. There's 1, there's 2, there's 3, there's 4. And this out here is a memory array. And so by making it this small, we were well in the way of creating something that would be implantable. Another piece that didn't exist very much was an electrode, in this case, a rigid electrode, where this is a stainless steel, this is a parylene overcoat, this is a polyimide tube, and then all the way down here, we have a carbon fiber, which is actually the sensing tip. And so we started out on our work like this, that carbon sensing had been used industrially for doing a sensing technique such as this. And so we were pretty happy with this. The carbon is actually a pyrolytic carbon. It's carbon fiber. And pyrolytic carbon is used in heart valves. And these heart valves are implanted in people 20 to 30 years. And they're fine. It works great. What we discovered is that in terms of the carbon fiber, this would be day 1. Here's day 3. You can see the reduction in diameter. Here's the plug type, so we're using the end of it. You can see that in relatively short order, there are these holes that are developing. The signal over here in day 1 is really quite high. That would be these areas. And after 3 days, you see the signal is going away. And so we're going, okay, this is new. And so the question is, what's really happening? Why is this the case? Because other people aren't getting it for other applications. And the reason appears to be that through the voltage ranges that we needed to apply to these electrodes were so high, it was past what was called the water window in the solution, which in this case, extracellular fluid. And what was happening is that when we had to raise the voltage so high in order to measure some of the analytes, we were getting the evolution of hydrogen and oxygen electrolysis. And the oxygen is highly reactive, and it was actually converting the carbon to carbon dioxide, which would be whisked away by the circulatory system and breathed out through the lungs. And so what we had thought would be a great value turns out to be something that, yes, you can use it for an extended period of time, because there are some techniques you can use to extend the lifetime. But at the end of the day, we need this to last the lifetime of patients, and that could be 20 to 30 years. Fine, okay, well, what do we need? It has to be biocompatible, it has to be oxidation resistant, it has to be carbon containing because of the association with the neurotransmitters. There's a whole variety of characteristics that this must have, and one of the important ones is also electrically conductive. And so when you run down the list of available materials, there really is not much that we came up with. In fact, the only thing that we could uncover was diamond. And diamond is an amazing material, but it's also something that is not electrically conductive. It's a wonderful insulator. However, if you remember the Hope diamond, so it's about a 43.5 carat stone. It's about that big. Right now it's in the Smithsonian Museum, donated by Harry Winston, a jeweler in New York City, who actually just put it in the mail to deliver to the Smithsonian. If you look at it, that the color in the blue diamond is caused or as a result of it being electrically conductive. So the free electrons that are in things that are electrically conductive in a clear material like diamond causes a blue color. And so in effect, what we needed to do is figure out how to make basically miniature Hope diamonds so that it would be electrically conductive and we could make our measurement. Here's a video that tells a little bit more of the story.
Deep brain stimulation is state-of-the-art neurosurgical technique where an electrode gets implanted into the brain. In the case of Parkinson's disease, we can instantly stop that tremor. One of the greatest challenges that we had was a durable electrode. Our division of engineering came up with the potential solution of using diamonds. These diamonds have very unique properties. And so the division of engineering built us a diamond reactor.
We thought about the process and said, we can do this. The members of the team included electrical engineers, mechanical engineers, programmers, glass blowers, a wide variety of team members. The team created this reactor in 4 weeks. We turned it on, and 4 hours later we had our first diamond. So that's an example of once you find a problem, sometimes the solutions are very straightforward. And so now we looked at our laboratory and said, okay, what are we really doing? Well, the research is really to improve neuromodulation therapy. So it was a bit more complex than we had once thought. And so we still wanted to develop a closed loop, self-modulating, kind of a smart deep brain stimulation system based on neurochemical sensing for feedback control. We needed to continue the development of the sensitive and durable boron-doped diamond electrodes for the neurochemical sensing. We need to develop advanced functional imaging procedures to assess brain activity because once we started stimulating, we wanted to see what was actually happening. We needed to continue the basic research to understand the mechanisms of neuromodulation therapy because even as of today, no one does not really understand how this is working. We needed to extend the use of neuromodulation therapy from the treatment of movement disorders like Parkinson's, which is very standard, to the treatment of psychiatric conditions like depression and addiction. And we also wanted to extend the use of the neuromodulation therapy to the treatment of spinal cord injury. And in fact, we have had some wonderful success in that area also. So we needed to reset our timeline. So here we are 10 years later, 2021. So what have we done? What have we got to do? Well, the laboratory prototype of neurotransmitter detection, check, we did it in 2011. Diamond production, did it in 2012. Integrated circuit, we got it in 2014. Absolute value measurement system, which we didn't think we were going to need, but it turns out we do. Got that done in 2018. 2020, we've got 8 patents and applications in process. 2020, we've got a production and marketing partner identified because you need a commercial partner or you have to create one to take this out to the world, to do the manufacturing and do the support at every hospital that wants to do this. So 2012, we moved that to 2022, a wearable system to corroborate the neurotransmitter levels and clinical outcome. 2024, we need to do the diamond electrode system. Okay, so in 2012, we've got the production, and now there's things that we're learning that we need to bring together into the system. In 2014, now moved to 2026, the implantable closed loop system. 2027, we anticipate applying and receiving FDA clearance. And in 2028, we expect to have it in use by patients. So our timeline has changed dramatically. The amount of work that needs to be done is increased exponentially, but yet we're very pleased to see that we do have an end in sight. So let's look at the finances of the Neuro project. After all, we are engineers and economics matters. So in 2011, we were estimating the cost would be about $10 million to complete the project, and the market size was estimated to be about $500 million. And so it could support, that market could support this type of a development expense. So let's move forward to 2021. Our estimated cost at this point is now it's going to cost about $90 million. But the market size had increased dramatically as we've been talking with people in science, in engineering, and in companies. And so the estimated market size could be as much as $4 billion per year. But our goal hasn't changed. We sometimes are asked, well, what sort of person are you looking for? Okay. And so this is the answer to that. And this has not changed for a number of years. We're pretty secure in this. And we need an engineer with a depth and breadth of knowledge, not a silo, but a much broader view of the world. And an ability and interest in lifelong learning, because things change. I mean, my original training was as a chemical engineer. I started out in oil, went to specialty chemicals, went to electronics, went to biologics, and then ended up in medicine. And so each one of those changes required a lot of knowledge to be understood. We need people with judgment and reliability. We want people to ask questions, but we want them to ask the right questions at the right time in the process. Yes, we do want people that take risks. We want people that take calculated risks, because every time you do a project or a development, it's expensive and it takes time. And things that we don't have in life are enough time and enough money. We need people that are creative and collaborative. Creativity is something, to come up with these new ideas, these new thoughts, these new directions, and collaborative to work with the teams in order to actually make it work. We need an economic and business orientation to understand the issues behind bringing in the funds, spending the funds, being efficient at that, and communication, because everyone needs to share the projects that they're working on and gain excitement from other people. And that's with the written and spoken word. Collaboration has been very important to us. And in terms of some of the issues of collaboration, we are looking with people that have a similar working style, a similar purpose in life. The needs of the patient come first is something that very much moves us at the Mayo Clinic. We need people with a high energy. We need people that are available. We need people with respect and convergence of goals, publication, intellectual property, confidentiality, and use. So as we have moved forward, we have created a company to create the conditions for the FDA approval and make a device that actually could meet the market needs. And so the company is now 3 years old. We have licensed the technology from the Mayo Clinic, which is the technology that was developed in the Neural Engineering Laboratory. And we brought people together that are more directed in terms of usability, of FDA approval, of the right type of experiments that the FDA is expecting, and at the same time give us the ability to interact with the market, to talk with potential users, and make sure the designs that we're coming up with really will have applications in the operating room. Those are things that we can't do within the Mayo Clinic. And Mayo has come up with what we call the Employee Entrepreneurial Program that allows employees to change the percentage of time they work for the Mayo Clinic and work for the company in terms of developing these things. So those timelines are now the combination of what we're doing in the neural engineering laboratory and what's happening in NaviNetics, as we call this company. And I look forward to speaking to you sometime in the future to tell you how it's gone. And so with that collaboration and starting at one side and moving to the other is when the miracle occurs. And so I'm looking forward to hearing your stories, and it's been an absolute delight talking with you today. Thank you.